Yes,
yeah, we had a couple of minutes. You know, we just start before. Okay. Why not? Give it a little pierce.
Yeah, I don't know whether. All right. Shall I start?
Yeah, right. So let me just, welcome everybody for our fifth day. So it's a pleasure to reintroduce Subir, who has already given a talk, so he scarcely need any more introduction, but of course, well known as one of the fathers of criticality, for whom his works in imagine approaches to spin systems, fractionalization, and all the rest. So pleasure to have you back here, and over to you for today's talk.
Okay, well, thank you very much. It's really been very enjoyable to be at this meeting and listen to all the interesting lectures. So I will continue and finish what I intended to finish last time, which is this new approach to a theory of the pseudo gap in the cuprates. So let me just summarize the theory and then conclude this part of the talk with some discussion that hopefully will be generated. Okay, so the idea here is to start with the Hubbard model and initially follow a very conventional route. You rewrite the Hubbard model as free electrons coupled to this boson, which is the paramagnon, a central actor in, for example, the theory of helium-3, where it's the ferromagnetic spin fluctuations that lead to spin triplet pairing. In here, we will be focusing on the antiferromagnetic component of phi. Okay, now it turns out to be very useful and important to rewrite phi in a Hamiltonian form. So what we do formally, this is an exact transformation. You take the Hubbard model of electrons and you rewrite it as a model of free electrons coupled to a double layer antiferromagnet. So we introduce these ancillar degrees of freedom, which is 2 additional square lattices, of which only a one-dimensional section is shown, coupled to each other by a coupling, antiferromagnetic coupling J-perp. And now in the limit of large J-perp, this is kind of a trivial insulator because the spins will just form singlets with each other. And so you can do a perturbation theory in 1 over J-perp to eliminate the sector of the Hilbert space. And that's completely analogous to the Schiffer-Wolff transformation, And if you do this, a little work shows you that you basically get the Hubbard model on the original system. And this is just, in the end, just another way to do the Hubbard-Stratonovich transformation in a more Hamiltonian picture. And now, now this particular system here of spins, the ancilla layer, has an excitation which carries spin 1, and this spin triplet can move around, and that is the paramagnon excitation. It'll have some wave vector dependence and where the minimum energy resides, and that will determine whether it's ferromagnetic or anti-ferromagnetic in the Brillouin zone. Okay. But of course, if all we were doing working at large J-perp, there's no point in doing this because we may as well work with the original Hubbard model. And now we're going to imagine that under renormalization, somehow we can also look at the regime of smaller J-perp and see what we get. So first, let's represent the phi in terms of spins. And phi is S2 minus S1, because that's the operator that creates the paramagnon out of the vacuum. If you want to go from a singlet to a triplet, you have to hit the operator S2 minus S1. S2 plus S1 does nothing, just give you 0. So that's the phi operator, and phi is coupled this way. So we just replace phi by this in here, and what do you get? So now you get a kind of a Kondo lattice model where there's one layer of spins coupled to the conduction electrons with an anti-ferromagnetic coupling, and another layer of spins coupled to the same conduction electrons with a ferromagnetic coupling. Now we know, at least for the single ion Kondo problem, that anti-ferromagnetic couplings are much more important than ferromagnetic couplings. Anti-ferromagnetics under RG go to infinity, was ferromagnetic coupling we go to 0. So we imagine that on short distances there's some renormalization, so that eventually JK, the anti-ferromagnetic component, this one, becomes more effective than J-perp. So yes.
The relative sizes of JK.
At the beginning, J-perp is much bigger, of course. That's where you can formally justify this. Yeah, well, so that, like I said a couple of minutes ago, we are going to, this is if you're at large J-perp and you work in the large J-perp regime, we just back to the Hubbard model. There's nothing new you can say. So we're just postulating that maybe you can use this mapping even at smaller J-perp. That JK could also be quite large, in fact, and under RG it's going to grow, and let's hope there's a regime. Yeah, well, okay, so so I'm not doing a microscopic calculation of a Hubbard model. That's a very hard thing to do, but we are hoping that there's a regime of this more expanded model where we can in control describe a different phase. That's right. If you're actually in the large J-perp regime, it's hopeless. I haven't done anything because I just read it in the Hubbard model. There's nothing new to say. You can go back to the old approaches. All right, so we assume that this coupling is more important than J-perp. That's an assumption. We just want to explore what kind of phases we get and see if that has anything to do with observations. Okay, so if this is much larger than J-perp under RG, it will grow, so maybe it becomes large enough. So let's imagine that we can just look at the effect of this coupling. Well, then you have just a good old Kondo lattice model that we studied in the heavy fermion context. And so what would you conclude? Well, you include the top two layers will form a heavy Fermi liquid state. And what would be the volume of the Fermi surface? It'll be the volume of the density of holes here plus the density of holes here, which is 2 plus P. But remember, you always had to measure things mod P. So this is actually P. So what was usually the large Fermi surface with volume 1 plus P now becomes, since the electrons themselves have density 1 plus P, now becomes a small Fermi surface of mod 2. Okay. But the second layer spin is there, and it's really required for the whole consistency of the theory. And so these spins, have some frustrated couplings along this direction, we hope. And so they must form a spin liquid. If they're ordered or does something else, well, then you just get a trivial ordered state and you're back to where you started. So if this second layer, so there's two ingredients. The first layer forms a large Fermi surface with the physical layer, and the second layer forms a spin liquid. And really, in some sense, the second layer forming a spin liquid is essential because that's where the emergent gauge excitations live. If you didn't have those excitations, you couldn't violate the Luttinger theorem. But now you are violating the Luttinger theorem because the physical electrons have a Fermi surface of size p, which is a violation of the Luttinger theorem. And that can only happen because, and that really requires the second spin liquid to exist. All right, so here's another picture of it. There's a spin liquid on the second layer, which some kind of resonating valence bonds. It could be any spin liquid you want, chiral spin liquid, pi flux phase, Z2 spin liquid. They're all allowed. And the top layer forms a small Fermi surface of size p. And this would happen in the limit of large jk over j perp. Whereas in the limit of small jk over j perp, you will get a conventional Fermi liquid state. I'll show that in a minute. But let's just discuss here. So this picture also shows you a very simple variational wave function. You write down a Slater determinant of hybridized electrons and the first layer. That's what you did for the heavy Fermi liquid state. So that's the Slater determinant of C and F. And then you write down some kind of wave function here, say a simple Slater determinant in a spin-on Dirac spin liquid, for example. So you would write down Slater determinant of F2. But now the novel thing and the hard thing here, which is numerically quite hard to carry out, you got to remove the degrees of freedom on this extra layer. And in the Gutzwiller projection, you just removed all W occupied states. Here you got to project these bottom layers back onto spin singlets. So you take any state. There are 4 states on these two sites, and you can write the 4 states as linear combinations of singlets and triplets, and you just pick out the projection onto the singlet sector for any state in the expansion of these two Slater determinants. So it'd be great to learn how to do that efficient numerically, and there are people working on that, but it's turning out to be quite challenging at the moment. Right. So that's but nevertheless, this is really the first trial wave function that we can write down for this FL star. And the point is that once you have done this projection, that is the second layer has been projected out into these singlets, then what's left over on the left-hand side are just the electrons. So this is a wave function of just the pure electrons. The ancillas were just there to write down this complicated wave function, but there's nothing on this side. It's just the electron degrees of freedom. So in that sense, it's very similar to these kind of PEPS wave functions that people deal with. Although here the difference here is we're dealing with fermions, and that's really crucial to get the right Fermi surface size. In PEPS, you always have these bosonic degrees of freedom locally. This is more like a fermionic PEPS. Okay, and then on the other side, of course, the Fermi liquid, where you just have a very simple wave function, it's just 3 fermions on the physical layer and singlets on the other layer. But even here, there's a question here. Is this projection a very innocuous thing? And so I'm not going to go into that. So that, just like for the heavy Fermi liquid theory, the way you address that question is by writing down a gauge theory and looking at the phases of the gauge field, and if there are any long-range effects in the gauge field, that's going to destroy a Fermi surface. So we've done that at great detail. Here you need an SU2 gauge theory because this projection involves an SU2 projection in the spin space. And you can also show that the SU2 gauge fluctuations have been appropriately Higgsed in this phase, so that in fact there's nothing singular and this small Fermi surface is stable. So ultimately that's the justification of the entire procedure rather than any formal analytic calculation. We can find a phase of this electron Hubbard model which is at least locally stable. So that's all we're saying, that there's we can write on a wave function which is locally stable. So there's a variational wave function that you can now play with, independent of whether you believe the derivation or not. Okay. Yes. Yeah. 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 Yeah, no, there's always anything you want. So there's some restrictions, however. You can only introduce degrees of freedom that are in some sense trivial, that can form a trivial insulator. And these degrees of freedom, can form this insulator here. There's a ground state, which is a product of local singlets. Or it could be a Philly-Phil band or something. So whatever ancilla you introduce have to have a trivial ground state. Otherwise, they will change the Luttinger theorem. They will change all kinds of basic things, or change the topology. They have to be topologically trivial, and even, if this is an interacting system, they should just be the product of singlets, product of local ground states. Yeah. So yes. So you could add any even number. You could add 2, 4, 6, 8. You could certainly add more, but you can't add an odd number. So that's the first thing. But another thing we're using here, which is also a feature of the Kondo lattice theory, these spins, if you go to a quantum computing company, that you can do this, these spins, they're just the qubits. But it's very important in getting this state here, this state, that these qubits be realized as fermions. At least that's what they end up doing on their own. I mean, you could put bosonic qubits here, but they hybridize with the conduction electrons and form this new Fermi surface. And that's rather an exotic thing for qubits to do, but they can do it. But in many of the PEPS wave functions that people have been working with, they don't have the ability to do that because they're using bosonic wave functions. Yeah. So we do have some calculations in certain models that I won't talk about. We have a calculation in a model where each of these layers is a random SYK spin system. So you make all the spin couplings random in all 3 layers, and then we can solve it. And in that case, we can show indeed this axis is doping. Numerically, you can solve all the equations. It's like a DMFT set approximation, and you can show this axis is doping, but only in that limit. Yeah. Yeah.
Just a nice question. So, this the liquid phase, like what are the kind of excitations you get? Like, and what is the
It's up. There's many possibilities. They're all open. I mean, so basically, another advantage of this whole approach is, for the past 20 years, we've learned a huge amount of the nature of spin liquids in insulators. You can have the simplest insulator, simplest spin liquid is the Z2 spin liquid, which has a Wison and a fermionic spin-on and a bosonic spin-on. Then there's a chiral spin liquid, which is semionic statistics, spin-on with semionic statistics. Then the other one is the flux phase, which is gapless Dirac fermions coupled to U1 gauge field. These are all allowed. It just depends on the details. And so, I would love it someday, my dream is that experimentally we will identify which one it is. And that would, neutron scattering can detect these spin excitations. So that's another important prediction of this approach, is that you get this state, which has 2 sectors. It has a small Fermi surface of size P, and that has usual spin and charge excitations of any Fermi liquid. In addition to those excitations of a Fermi liquid, you have the spin-on excitations of a spin liquid. And another advantage of this approach is that you can just use that theory for insulators unchanged. You can just import it. You don't have to do anything. There's been enormous effort in the last 20 years on doped spin liquids and trying to find different studies of doped spin liquids. And it's led to very different predictions that don't agree with experiments. And I'll summarize that in a minute. Yes.
So you mentioned that the tensor network methods can't really cope with this because they don't deal with fermions. But in one might think of a 1D.
I mean, this is a tensor network wave function down here.
Yes.
The
lower part.
Yes.
If you were to take a 1D model and turn the fermions into spin,
Yeah.
what sort of spin model does that look like? Because that is something that, and then what does this phase at the bottom look like in such a picture? Maybe it's a spin phase.
Well, I mean, in 1D, we have a lot of technology. In principle, we're claiming this is a phase of the Hubbard model. So you could just start with a 1D Hubbard model and dope it away from half filling. Perhaps you need some near neighbor exchange couplings and so on. And there are in fact, classification of 1D metals you can never violate the Luttinger theorem in 1D. There's an extension of Luttinger theorem proven by Yukawa and Affleck, which always holds. But still, there are many different types of metals. You count them by the Fermi points of the spin and charge sectors and how many gapless sectors you have. There's a CMSN classification, you may know, of a number of gapless charge and spin modes and at what momenta they appear.
I guess I was
asking
if you turned it into an entirely spin problem. What would be the image of those different types of metal as spin problems?
Well, I think I'm answering that question, but I'm trying to use a more invariant language. So you're going to get some Luttinger liquid, but there are analogs of Luttinger liquids in 1D in which you can say this is the analog of FL and that's the analog of FL star. They differ in the number of spin modes and charge modes, but the wave vectors of the spin and the charge modes obey a Luttinger-like theorem, which is a generalization of the usual Luttinger theorem, and that's always obeyed. So it's not, fractionalization in the sense of 2D and emergent gauge fields in the sense of 2D do not exist in 1D. And we have a paper soon to come out, which is going to describe the 1D not by the methods you're suggesting, but by bosonization traits. Yeah. I don't know. Did I answer? Maybe not. Yeah. So let me just summarize. So the many papers, including many by me, so I'm guilty as charged. When they do a theory of the doped spin liquid, what they do is you take the electron or the hole with spin 1/2 and charge E, and you fractionalize it into something that only carries spin, and this something that only carries charge. This is the famous spin charge separation of Bhaskar and Anderson. This could be fermionic and that could be whole bosonic, either way. But the bottom line is the trouble with this approach is that this particular hold-on has never been seen. There's no experimental indication of any charge carrier that doesn't carry spin. I mean, not at any temperature. It just hasn't been a reasonable description of anything in the experiment. So, okay, fine. So that's what, and you don't want to do this. The reason you don't want to do this is because T is much bigger than J in the TJ model. If T was much smaller than J, this might be a reasonable thing to do. But when T is much bigger than J, it's highly unreasonable because it's the energy J that wants to fractionalize, but it's the energy T that wants to bind. I mean, the T term in the TJ model is a strong attractive potential between the spin-on and the hole-on. It's like F dagger, B, F, B dagger. It's like an attractive force. And if T is much bigger than J, the hole-on will always find a spin-on and bind with it. And there's also a lot of evidence from cold atom experiments that always happens. But Eugene Demler may have talked about it earlier this week. So what are we doing? Well, we are saying, no, something slightly different. Any electronic system also has these paramagnon excitations, which is spin 1 and charge 0. So there's no charge here. And when there's no charge, then go ahead and fractionalize. And you can fractionalize into 2 spin-ons, and that's the theory you're proposing. Okay. All right, so now that we have this scenario, we can at least do some mean field theory, see if it works. So in the very simplest mean field theory, we'll fix that in a minute. You just even completely ignore the second layer. And then you just have a good old Kondo lattice where you have, these F1 fermions that can hybridize with the conduction electrons to form a large Fermi surface. In this case, as I said, the large Fermi surface is really small because of the mod 2. So you just go ahead and do that. You just take the old theory by Pierce and others of the Kondo lattice. So you have the conduction electrons, then you have the spin-ons. This is the spin liquid sector of the first layer, and then you hybridize them with this. So you condense this B, and when you condense this B, a lot of the gate symmetries disappear. So now we have a bunch of free parameters. The Tij we know. The T1, we take first, second, and third neighbor, and the B are free parameters. So we're going to treat these 4 free parameters and try to fit a lot of data. So it's all, I hope you believe me, it's highly overdetermined, and no one has succeeded in fitting everything by fewer number of parameters, or even more, actually. There is one constraint which comes from the theory that the F fermions must be exactly half-filled. So that there's a chemical potential that's determined by requiring the F to be half-filled. All right, so here's the actual physical Fermi surface. The red line is the Fermi surface of the Fermi liquid phase at high doping, extended to lower doping. We know these T's. The T1 gives the dashed line, which is exactly at half filling of the Fs. And in fact, here this Fermi surface is electron-like, and that's hole-like. When you hybridize them with the B, you get the blue line. And so here's the photo emission prediction, and it's much lower intensity at the back than the front, simply from matrix elements that come from this diagonalization. Okay. And this is to be compared with the experiment, where they, of course, only see the front side. There's no observation yet of the back side. And I believe this is because of this order, but, it'd be nice, of course, to see the back side. With this experiment of Peter Johnson claimed to see some indication of a turnaround, completely consistent with what we have here. I should also mention, there are similarities to this, at least at this level, to the YRZ picture, which we had also worked on. With some important differences, we have fewer constraints or different sorts of constraints on the Fs. Okay. All right, so that's what's happening in the nodal region, where we can at least get the Fermi arcs. And at this point, everything is fixed. We know all the parameters. And so let's go to the anti-nodal region. So here you have a gap. And let's look at the dispersion along this direction. Okay, so this is what you see in the experiments. You can only see the spectrum below the Fermi level along this. So this axis here, the horizontal axis here, is the same as that axis. Okay. The red line is what you see at high temperatures on the overdope side, so ignore that. The green line is the superconducting signal, so ignore that. The important signal is the blue line, and it's got this feature, and this energy here is the pseudo gap. Oops, this is the pseudo gap. And there's nothing crossing the Fermi level in the underdoped regime. The blue line doesn't cross the Fermi level. So one important thing pointed out in this paper by ZX Shen's group is that this KF2 and KG2 are not the same. They're shifted. If this was some kind of superconductor, this is the normal state, and that's the superconducting state, KF2 would be equal to KG2. So they are shifted. And the fact there's a shift is what's led at least Patrick Lee emphasize this shift in proposing a pair density wave state. Okay, so in our case, we can also get the shift, but from a very different picture. We just take the same band structure here, take exactly the same thing, but you don't have any free parameters left. And so in this case, the red line is the parent Fermi surface. The dashed line is the ancilla Fermi surface, ancilla dispersion, excuse me. And the blue line is the hybridized structure. So it's this blue line here that's shown here. This is the theoretical calculation, which is to be matched to this blue line here. Okay, and you get a shift. You can see the shift right away. This point here is different from that. And the reason that's happening is because the dashed line is at half filling. That's the first ancilla layer. And this red line is at filling 1 plus P. They're not the same. And that's what gives you a shift. Okay. All right, so that's something we can also get. But there's something more. We can also look at the nodal region. And if you look at the dispersion on the nodal region, okay, this is now the dispersion, I think, going this way along the node. What you see, the red and the blue lines in the data are exactly the same. That basically there's essentially no difference between underdoping and overdoping in the nodal region. And STM also has very similar data. But this is data, yeah, okay. And that's exactly what comes out of our theory. If you look below the Fermi level, the red line and the blue line are basically the same. On the other hand, in the pair density wave theory, if you do this away from the Fermi level, it's a total mess. There's a lot of structure here that's not seen in the experiments that comes from the pair density wave theory. All right, so now finally, we want to put back this missing spin liquid layer, which is really required by the structure of the theory and the whole YRZ type construction, and was not in the YRZ theory. So here we just take a very simple point of view. We take some nice spin liquid, like the one I talked about last time, this gapless Z2 spin liquid. That's some choice. And this will couple to the small Fermi surface by this coupling here. And the J perp, in fact, which is a large coupling, we'll just treat it perturbatively and compute the renormalization of the physical electron spectrum from these spin fluctuations. So this will renormalize, these type of excitation. These excitations far from the Fermi level will shake off some spin-ons, and that'll broaden the lines in momentum space. And so you can look at the MDC and the EDC of these lines due to these spin fluctuations. So this is a much more complicated calculation. You have to do big integrals over momentum and frequency space, done by Maria and what's his name? I should remember everyone's name. Excuse me, it's my age. I forget people's names. Oh boy. Eric Mascot, I remember. Eric Mascot and Maria Tiganovskaya who did this calculation. Sorry. Okay. And so, there are new free parameters here, so I don't want to make a big deal of it. But, here's some EDCs and MDCs. This is the calculation, this is the data. And it all, it was really relatively effortless. The first thing we do is gives you the shapes completely consistent with what's in the experiments. Anyway, the hope, of course, would be eventually there can be neutron scattering studies, and we can really identify these extra spin excitations that are required to be there in the underdoped side. All right, so let me just conclude then the talk that I began last week, on Wednesday, excuse me. So I've given a new approach to think about the theory of the FL star of the pseudo-gap metal, the underlying physics is not different from things people have talked about for 20 years. But the novelty of this approach is we never talk about fractionalizing the electron. We always keep the electron intact, and we fractionalize the spin degrees of freedom in a nice way to get small electron pocket. And we're very happy. Hopefully, I've convinced you that it rather effortlessly just agrees with existing data. So what's for the future? Do we predict anything, and can we really settle this? So of course, it'd be wonderful to see the backside of the whole pocket. And you could just say, well, it's a high temperature state, and maybe just the intensity is too weak. But recently, people have seen the backside in the ordered antiferromagnet in cleaner samples, and maybe that's possible here. I also mentioned last time one of the the very important outstanding problems with the theory of the cuprates, which is the understanding of the quantum oscillations, which are predicted to be, which are observed to be those of a single electron pocket in a regime where there's long-range charge density wave order. This is 30 Tesla and above. There is no real theory for it. And I think our approach, and this is something we are working on right now, gives us a way of getting exactly this structure. So the picture here is that you have an intermediate temperature, and that you're in this FL star state, but as you lower the temperature, there's always confinement. You confine and you get the CDW state, but the nature of that CDW state cannot be understood as a CDW on a Fermi liquid. It's really a confining CDW on an FL star state. Of course, it'd be nice to see deconfinement all the way down to 0 temperature, but we may not be so fortunate. I mean, let me also say, like the gauge theory for QCD is also exactly like that. You only see the fractionalized excitations at high energies. At low energies, there's only baryons. That may well be the fate of many fractionalized phases in the real world. So it'd be great to see neutron scattering observation of spin liquid in the second layer, as I said. And there's certainly a lot of evidence in neutrons that there's a whole sector of spin excitations in this metal that has nothing to do with the Fermi surface. So more careful studies hopefully again. And I think a lot of theory is needed here too. Finally, I haven't discussed at all the nature of the FL star to FL transition. We have papers on it, but there's a lot of work to be done there, and hopefully further contact with experiments. Okay, so that's all I want to say on this topic, and I will turn to somewhat more general theories of strange metal in a few minutes, assuming there are questions and discussions. Yeah, so I'll pause for questions on this and then start the next talk. Yeah, go ahead.
Why would you think the observation of whole pockets? Why is it just, I'm not sure how many observations are made, but why is it consistent in the backside of the sheet rather than any other pocket?
Well, I mean, the theory, yeah, so the theory says that this is the front side is more intense. This is a theory calculation. And the reason the front side is more intense, you can see from this picture. So this is the electron Fermi surface, the C Fermi surface. This is the F Fermi surface. And then you hybridize them. And now you see in the front, you're closer to the red line. And so you have more intensity. In the back, you're more like the F, and you have just a little bit of C. So there's an energy denominator there, and that's what suppresses the back. Right. So, so if you look at the cuprate phase diagram, well, no, that's ahead. In the cuprate phase diagram, oh, that's my next talk. Here. There's the AF insulator. So you could go in here and look for the pockets. They're conventional pockets. And there, until last year, the backside had not been seen. But now it's been seen. It's really very beautiful experiments, and they're only seen in using some very clever tricks to reduce the degree of disorder by making these multi-layer samples with looking at the inner layers, which are very far from the dopants and so on. So, all right. So that gives us hope that someday the backsides of this will be seen. Yeah.
Do you think there are any oscillator experiments that help see the specs in okay, like just doing some experiments?
There could be. I mean, that's an interesting idea. I mean, there's, of course, the Emmanuel Bloch and Marcus Greiner have fermionic Hubbard atoms, and they measure very different things. So there is already a paper. I don't know. Maybe perhaps Eugene talked about it, where they measure, multi-point spin correlations around the hole, and in those experiments, I mean, they're not measuring the Fermi surface because it's a very different measurement. It's not a zero energy measurement. It's a local time measurement. And so you have a lot of spatial information, but you're integrating over all frequencies. To see a Fermi surface, you have to do a scattering experiments at low energy. So perhaps they'll do something yeah, it's possible. But in any case, in what they have already, they see even with those relatively high energy probes and also measured at rather high temperatures, they see that there's a dramatic difference between low doping and high doping in the metallic state, in the nature of the local spin correlations, where these can be fit to Fermi liquid, and these, I mean, Eugene and collaborators have a theory of what they call polarons. They have these spin charge polarons, but in the present, and that's entirely consistent with the FL star state. The polarons in this picture are just the renormalized quasi-particles of the FL state. But their theory so far is just of single polarons, not a finite density of. This is a theory of finite density of those polarons. Yeah. Yes, Seamus.
So why is it that undergoing the quantum oscillations?
Okay, I discussed that last time, but great question. Yeah, so
Just which quantum mechanical object is responding to
yes, great question. So let me just tell you the picture of Harris and Sebastian. In the Harris and Sebastian picture, there are these Fermi arcs here, and that's these things here in your data, and so the electron, is moving along this arc, and then it scatters to this point by a CDW. Then it moves along that arc, and it scatters to that point as CDW. So you need these two Q vectors for a CDW, which presumably is present here at very high fields. And then so if you mod out the Qs, then you get this red pocket. Okay. And that's what's doing the quantum oscillations. Okay.
They are honest electrons.
Yes. Yeah. Absolutely. Yes. So, but what's the problem? The weakness of this theory, the problem with this theory is that there is no underlying, the starting point itself is questionable. You can't take a theory of an arc. If you take a theory of a full Fermi surface and you put the same Q vector, which they did that too, and we did it more carefully, you do get the pocket. We agree you get that little pocket, but you get a lot of other stuff. And subsequent quantum oscillations, where many people have never shown sign of any of that. I think there's a paper by Suchitra also showing, by looking at the form factor of this oscillation, that there's only one pocket, period. So what do you, how can you get just one electron pocket? I mean, that's really the fundamental question. And the answer, as they assumed, phenomenologically, maybe there's no Fermi surface here. Well, so how the hell do you get rid of the Fermi surface there? That's what the theory of FL star is about, how to get rid of the unknown part. So now what we would like to do, and we're hopefully we will have a paper with some details on this. What we would like to do is start from this FL star state, which gives you this Fermi surface. So we're going to start from this state. So there's now there's a nice gap on the antinodes. There is still the backside, but it's required for the consistency of the theory. And we're going to put a CDW on top of it and confine this, see what we get. That's what we're working on. So that would be at least an internally consistent theory of the observation, of which there is no current theory. Yeah.
So at an agnostic level, I suppose what we're predicting is the presence of holes in the self-energy of the original electrons, right? I guess.
I don't like that language, but go on. Okay. Holes in the
meaning if I could do a calculation of the Green's function in this system, I would see zeros in the Green's function.
No, I don't see that. That's not true.
The holes in the self-energy coming from your head.
Yeah, there's no such thing as zeros of Green's function anywhere in this theory. So there's a long discussion of this in my forthcoming book. No, that's an approximate picture. Yeah.
And those electrons have a dispersion with the Fermi surface defined.
If you compute the Green's function as in this theory, with the dispersion in the F sector and the proper chemical potential, there's no zeros anywhere. There are incipient zeros, which are lifted by the shift in the chemical potential of the F and the dispersion of the F. That lifts always.
If I take your two-band model defined by
Yes.
the C's and the F,
Yeah.
and I integrate out the F,
Yes.
that will induce holes in the self-energy of the C's with the original part.
Let's
Those
one
are the
second.
original electrons that were there. Those are the ones on the single Fermi.
I know. Well, yeah, but let's see. Yes, so you can write it that way. But those poles are, well.
Holes in the self-energy are zeros in the Green's function.
Yeah. No. One second. At this level, I guess there will be the bare dispersion of the other electron very far from the Fermi surface. They'll be along this line. Yeah, but that's some high, eventually that's going to be smoothed out somewhere, but go on. Yeah, in this approximation, okay, you're correct.
A number of DMFT studies do actually see holes in the self-energy.
No, they don't. They're again, I have written a paper with Antoine George studying all of this, and I think he agrees with me at this point. Those are lifted by any kind of inelastic scattering. They're completely lifted.
Sharp. Okay, whatever. This comment.
Yeah, no, I guess there's a forthcoming paper by.
They show very sharp peaks in self-energy.
Yeah, there are peaks, but they're not infinite. Yes.
Cool.
Yeah.
The scatterings are not exactly on Fermi.
No, in this theory, there are poles, but once you go beyond this theory, this approximation, there's no poles. They can be high intensity, but that means it's almost impossible to observe because the Green's function is practically zero there, as you said. It's not what you'd see in any experiment. There's nothing to do. And certainly that pole has zero to do with the violation of latent theorem. Those papers that claiming that has something to do with the violation of latent theorem are just incorrect in my opinion.
I didn't want to just want to pin down what the structure of self-energy.
Okay, fair enough. No, you're right. Okay, thank you. But you can imagine why I have this allergic reaction to discussion of poles. Which, sorry, I didn't mean to impose that on you. Yeah, go ahead. Yes, I mean, then you'll get a magnetically ordered state. Yeah, so in fact, yeah, well, I mean, so what you could imagine saying, you have the spin liquid here, and now these spin excitation could condense, and it gets a kind of ordered state. what is the nature of that transition, and so on. Yeah, but then you're back to some kind of state with long range order. No, it does. I mean, that's what's happening at lower doping, of course. There is, if you're interested in understanding what happens as you go from the pseudo gap this way, then that's what's happening here. Yeah.
Sorry if you said
No problem.
to what extent you generalize this. It would be greater idea, maybe be like manipulating ancillary degrees of freedom and preserving as much as possible. You're starting point,
Yeah, I mean, I think the main idea is that when you have a mobile electron whose hopping matrix elements T, maybe I can write this and use this thing. Okay. So, right. So if you have, you have some system with a mobile electron, so Tij, C dagger I, Cj. So you do this fractionalization where you write Ci, for example, as a fermion with a spin. Sorry, let's put a spin label and a boson. So this is the Bhaskar and Anderson spin charge separation, and then there's a Jij here, Si dot Sj. So then what you just make the substitution in here, and then you get Tij. Well, F dagger I alpha, Fj alpha, and then B I B dagger J, and then this gives you a Jij F dagger I sigma Fi times F dagger J sigma Fj. Okay, so that's the spin-ons giving you the spin interactions, and this is the hopping T. Now, if you were an insulator, we don't have this term, and this, that's a spin system, and like solid helium-3 or some frustrated antiferromagnet, that can certainly, we now have a lot of good evidence this kind of system can form spin-ons. All right, so let's say we take that system and we dope it. And the question is, will this kind of approach tell the spin-ons can survive? But this simplistic approach, popular approach, tells you that the electron falls apart into the spin-on and the holon. Is that a reasonable thing? So that requires a further step, which is, here to imagine that as they hop around, the spin-ons and the holons move separately. But if you look at this term, this is like a very strong attractive interaction between the F's and the B's. There's an F and a B, and there's a very strong attractive interaction, which is T. And so they'll like to form a bound state. And that bound state is precisely the polaron that Eugene, I think, discussed earlier this week. And really the point is that this T is much, much bigger than J. So you're faced with this awkward situation. You fractionize the spin-ons, and then you introduce these holons, and then you say, by the way, this holon isn't really there, so let's form the polaron, but let's keep the spin-ons around. That summarizes 1,000 papers, including a few hundred by me. No, not that many. But that's a very hard thing to push through, to first fractionalize and then do this binding. And no one's ever done any calculation to completion the way I've just shown you can be done with this new approach. So the bottom line is that this is the thing. If your hopping matrix element is bigger than J, you're not going to see spin charge separation in this sense. Yeah. Yeah. Yes, I could. I mean, but that depends in great detail on precisely which spin excitation, precisely which spin liquid you take. But for the pi flux phase, or get large peaks near pi, but the details, line shapes will be different in different. Yeah, and we need to think more about it. Yeah, so I'd love to talk more with Stephen on that question. Yeah, I think there's definitely a very interesting direction for future studies. I mean, there is this work by Henrik Renault, I think, and in Denmark, if I remember the name right, where they looked at these square lattice CFTD, I think, at high energies, the spin wave spectrum at high energies, and they found that in the insulator, where they found there was a very good fit to the pi flux phase and the spin-on excitations thereof, much better than the spin wave theory. So one of the simple predictions of those high energy excitations that I think Henrik Renault saw in CFTD will continue in the dope system, possibly even to higher doping. Yeah. I mean, we need to, they might be getting increments, right? And we'd be happy to think more about that. Yeah. Other questions? All right, so I have to finish at 11:20. Is that right? Yeah, okay. Well, great. We had great discussion. I hope you enjoyed that. And there's definitely more food for thought. And I'd certainly be very happy if people were interested in, working with this new wave function anyway. Where did it go? Anyway. All right, so let me go to the next part of my talk. That's here, the strange metal. Okay, so this is another, I mean, ultimately, this part is, we hope, connected to the previous part. There is, some kind of exotic metal state here, and then there's a Fermi liquid here. And the most natural conclusion is that strange metal in between has something to do with the quantum phase transition. But what's also clear is that the strange metal in some ways is a lot more universal than the pseudogap metal. The pseudogap is rather special to the cuprates. You don't see a pseudogap with a structure everywhere. But the strange metal seems to be everywhere. It seems to be like a more general beast. And so perhaps there's a more general theory, some very simple general theory that can tell you something about the strange metal. And the most dramatic consequence of the strange metal is that the resistance is a linear function of temperature. So here's some resistivity for LSCO. This is twisted bilayer graphene. You can look at pnictides. You can look at many materials. You can look at heavy fermion compounds, and they all seem to have this kind of linear resistivity. One other thing I should strongly emphasize is that a strange metal is different from a bad metal. A bad metal is resistivity at high temperature, where the resistivity is bigger than the mod Phi of E Regal value. So in 2 dimensions, that's just H over E squared. So if your resistivity is bigger than H over E squared, and you have something linear in T, that's also quite common with bad metal behavior. But it's very different physics. I think we have many successful theories of bad metal behavior, but essentially no theory of strange metal behavior where this resistivity is linear in T and much below the mod Phi of E Regal value. So that's the gene I want to focus on and propose an explanation. Yes.
So what temperature does the strange cuprate metal and the bad metal?
It depends on the materials, I guess.
Do you see any distinction experimentally?
No, you don't. No, you don't. So that's the next step of the theory, to understand why the two slopes are quite similar. And my former student Avishkar Patel, with whom I have worked on this project, has a paper on his own on that question. But I'm not going to answer that question. You can look at his ideas on that. But that's a second mystery. That once you have a theory of strange metal, why is it that there isn't much of a change as you go from the strange metal to the bad metal? It can be so.
I would like to know what the difference is so we can see the
Okay.
based on observations. In these systems, they're both
Yeah, okay. Well, okay. But any theory of there are many theories of bad metal which completely break down as you go across. Yeah. Yeah. So we want to have, yeah, we worry about how the theories meet later. Fair enough. Good question. But Avishkar is thinking about it. Okay. So the framework we're going to use is use ideas from the SYK model, which is a solvable model of a metal without quasi-particles. That's really why I think you should be interested in it. So it's a model with just random interactions, U alpha, beta, gamma, delta, are just independent random numbers. That's really all you need. And you can have any distribution you want. And there's no hopping. Then we can add hopping later, but let's look at this particular model, which you can now solve in the regime where you don't have any quasi-particle excitations. That's what's unusual about it. And then you can also check your calculations with numerical studies, and it all agrees beautifully. So that's a very useful thing to have. So how does the solution proceed? Well, at some level, it's extremely simple. You just expand the Green's function in powers of U alpha, beta, gamma, delta, and then you just do this average order by order, and you just count factors of n. If I had more time, I'd spend a little bit more time showing you how that happens, but there are many other lectures of mine on YouTube that you can find with more details. Let me just say that. So when you do all of that and the dust settles, you get a very simple equation for the self-energy. The self-energy is the product of 3 Green's functions. So there's just one graph that gets left over. Everything else is suppressed by powers of 1 over n. And this graph is sometimes called the Mellon graph, and it's about a U squared. But the very important point is that these are fully renormalized Green's functions. These are not bare Green's functions. So there's Mellons within Mellons within Mellons. Okay. So this is the set of equations that were first obtained by us for a somewhat different model. And these equations, so everything I'm going to say well, almost everything I'm going to say now is just a consequence of the applied math problem of solving these equations. You have some complicated integral differential equations here to solve. Initially I thought, well, that can't be that difficult. But the remarkable thing is we're still learning new things about the solution of these equations, and including the fact that these equations contain within them a version of quantum gravity. Okay, but I won't go into that. All right, so the simplest thing you can do, which we already did in 93, is show that the Green's function has a 1 over square root of tau decay. Local Green's function, unlike the 1 over tau decay that you get in the Fermi liquid. All right. Since then, a whole lot has been learned. I'll just summarize. You also find it has omega over t scaling at finite temperature. You can prove there aren't any kind of quasi-particle decompositions. And this is more recently, there's been an understanding that there's a kind of an emergent time reparameterization symmetry, which is only softly broken, and this controls the very low energy fluctuations. So if you want to read about all of this, there's an article soon to appear in RMP by Devanjan Chaudhary, Antoine George, Olivier Parkelet, which I encourage you to look at. And the whole question of strange metal, bad metal, Pierce's questions, there's whole sections there discussing this with lots of data, so you can judge for yourself. All right, so one of the amazing things is that this low energy theory for this time reparameterization mode is identical. This is a theory of quantum gravity fluctuations of a charged black hole in 3+1 space-time dimension. That is, in our universe, just take the Einstein and Maxwell theory. The only thing you require is that the black hole have a charge. which unfortunately is highly unlikely by any actual black hole out there, but it's, called a Reisner-Nordstrom black hole. It's at least a stable solution of the Einstein-Maxwell equations in vacuum. Okay, so one of the results that's come out of all the work on the SYK model, which I'm quite proud of, involved the work of many people who are all cited in here, is that we now, for charged black hole, we have an understanding of the correction to the Hawking's formula for black hole entropy. So if you can express black hole entropy or the entropy of any system in the microcanonical ensemble as the log of the density of states. So what Hawking argued that the log of the density of states of a black hole was the area divided by 4 in Planck units. This is the area of the horizon. But he didn't specify what the energy dependence should be. In string theory, there's a delta function. We now know that's not correct for non-supersymmetric black holes, and this is the universal answer. It's a sinh of the square root of the energy. And this came out of studies of the SYK model. Okay. All right, so that's a lightning introduction to SYK models. But so there's been a lot of work starting from this rather artificial model and trying to get a theory of a realistic strange metal. So it's all very nice work reviewed in this article. And if you just take SYK model and just make it finite dimensional as written, but there are many ways of doing it, you end up with a theory of a bad metal, but you don't end up with a theory of a strange metal. You end up with a bad metal that becomes a Fermi liquid as you go to low temperature. However, there's another approach that's been far more successful, which is what I want to tell you about. And these are what you can call as Yukawa SYK models. So this is not a theory just of fermions interacting. It's the theory of fermions interacting with the boson. So this boson could be anything you want, and depending on which paper you're reading, it could be a phonon, it could be a gauge field, it could be some kind of autoparameter. But there's some bosonic mode. So the idea here is, in addition to the electrons, there's an emergent bosonic mode that's low energy. And that seems very physically much more reasonable in a way, because anytime you see strange metal behavior, you're either near a quantum critical point or some Mach phase with spin liquid behavior. It's a regime of strong correlations where anybody's microscopic approach has some boson playing an important role. Okay, so if you look at models of this type, and now you make these Yukawa coupling, the G, which is only a 3 indices, a random function, then you can solve these models. And the remarkable result is then that the saddle point equations, I mean, of this model are exactly the Migdal-Eliashberg equations. Originally these were satisfied for weak coupling in the electron phonon problem. That's how they justified. But now this is in the strong coupling regime. G can be as large as you want, and at least so the SYK approach, or the Yukawa SYK approach, gives you for the first time a large N expansion for the Migdal-Eliashberg equations. So there's this very nice paper by Ilya Estelitz and Jörg Schmalin, who looked at a very simple model of fermions, there should be an I there, coupled to just an bunch of Einstein oscillators and Einstein oscillators with some frequency omega naught. And then these are the Migdal-Eliashberg Yukawa SYK equations. As Jörg put it recently in a talk he was giving, these are not new equations. They were written down a long time ago. Just nobody ever bothered to solve them completely in a self-consistent manner because it didn't seem like a reasonable thing to do. Well, certainly for these SYK models, that is what you're instructed to do. And when you do it, you find non-Fermi liquid behavior with some power law exponents in the fermion and the boson sector. This exponent delta given by some equation. So here's a phase diagram from their paper, there's some at low energies, there's some non-Fermi liquid state, which in fact even goes superconducting, but I haven't discussed that. All right. So what we'd like to do is to start from models like this, which we can solve, which don't have quasi-particles, fermions coupled to bosons, and make them realistic, and as realistic as we can. And use the same trick of using this large N approach to solve them. Okay, so this is a well-known and well-studied problem. So a realistic system would have a Fermi surface and be coupled to some critical boson. So this could be now a nematic autoparameter, a gauge field, some emergent boson in fractionalization. Doesn't matter. The theory in the end turns out to be rather similar in all of these cases. That's at least one relief. Okay. So for example, if you had nematic ordering, you have some Ising autoparameter phi, which when it's non-zero distorts the Fermi surface into some orthorhombic state from a tetragonal state. So then at finite temperature, you can imagine this type of phase diagram, where there's some finite temperature Ising nematic transition. You go from orthorhombic to tetragonal, and you're just breaking XY symmetry as you go from here to here. And so you would expect this to be just an Ising phase transition at long enough distances, and that is a correct conclusion. But we are interested in this critical point here, where there's a quantum phase transition from the Ising ordered phase to the Ising disordered phase. So the very first guess would be, well, just add a time direction because you're Ising, because you're quantum, and so it should be 2 + 1 dimension, 3-dimensional Ising criticality. That's not correct because they are fermions. That includes, which also give you low energy excitation that couple to the Ising autoparameter. Anyway, so this theory of at this critical point has been studied again in hundreds of papers, and there is a correct conclusion that you get a non-Fermi liquid with no quasi-particles, which has some similarity to the SYK state, as I'll show you in a minute. However, the further question you can ask is this orange region here, the quantum critical region, give you a theory of a strange metal, which I've defined as seen in experiments. That certainly is a claim also made in numerous places. And the answer is clearly no. I'm going to argue now. And we need to, this theory as stated is missing a very important ingredient. It's on a perfectly clean metal. So we're going to argue that in a perfectly clean system with a perfectly clean quantum critical point, you cannot get a strange metal. And you need some important contribution from disorder that I will present in a few minutes. Yes.
So you're thinking of nematic distortions to save these spins.
Well, there's long range order, and this is a collective transition for in any system you want. One phase has a ground state with tetragonal symmetry. The other phase has a ground state with orthorhombic symmetry. So, and it's a metal. So, what's that other? There's a ferroelectric transition, and what's that material that Gil Lonzerich has been studying? That's an insulator. So I'm not talking about that system. That is really a 3-dimensional Ising model or 4-dimensional Ising model.
But you're not thinking about distortions in one direction, so the spin up and spin down.
Spin plays no role here. This is you could have spin orbit or not. This is just a structural transition driven by electronic correlations in any system. The presence or not of spins shouldn't make any difference. But you need a Fermi surface.
You're not getting singular effects of the positive fluctuations.
Yeah, no, that's exactly what gives you this physics. Yes. The particle hole fluctuations make it a non-Fermi liquid. Yeah. But a non-Fermi liquid without quasi-particles is not necessarily a strange metal. I'm defining strange metal as an object that has a linear deresistivity. or any anomalous resistivity close to linear.
I guess I'm asking, do those fluctuations that drive transition first orders?
It could be, but let's say that's a very weak first order. But for the Ising nematic, I think there's a lot of experimental evidence that it's second order. Yeah. Yeah. So yeah. Okay. Yeah, that's fine. They could do that, but in some, not all cases. Yeah. But you still have the same problem. You don't have a theory of spinning metal, I claim. All right. So what am I doing? Yeah. So let me just show you what people have done in many different contexts. In the gauge field context, on the nematic order parameter, the theory is in the same, pretty much the same. So as Andrew mentioned, you get particle-hole fluctuations of the fermions, and that give you a Landau damping of the boson. So the boson Green's function has this form, and you take this Landau damped boson and you scatter it off the electrons, and as Patrick Lee first argued in 2+1 dimensions, you get this very singular self-energy for the electrons with a power of omega to the 2/3. So the SYK model has a power of 1/2. This is 2/3. Okay, it's a little different, but it's similar in the sense that the momentum, this has no momentum dependence, singular momentum dependence. That's much weaker, and so it's like a local self-energy with a power omega to the 2/3, and so that's very exciting. Okay, but this is a somewhat non-systematic calculation. And you would say, well, if I want to now do corrections, I need some small parameter. So you can try to introduce some labels on the fermions, say n labels on the fermions or even on the bosons. A lot of people have tried that. And in particular, a very nice paper by Syk Model has shown that none of it works. There are singular effects that are not controlled by 1/n in this type of theory. And we don't have any understanding of the full structure at this point. All right. So in our recent paper, we said, well, let's apply the trick of the Yukawa SYK approach. We said, well, we'll take this coupling G, which is here, and make it a random function of the indices of both the fermions and the boson. Notice this randomness is not in space, it's in some fictitious flavor space. And so you just take some model with some GIJL. Now you might worry that that's some other different model and everything will depend on the GIJL, but the hypothesis is that it doesn't, that at low enough energies, you flow to some RG fixed point, and you flow to that fixed point no matter where you started, or at least some large domain. So since the low energy theory is the same for any values of these couplings, well, you can make life simpler for yourself by just averaging over all couplings. So, okay, so that's the trick, which is very much inspired by all the successes of the SYK model, where precisely the same trick has led to all kinds of results, even for systems without randomness, like black holes. Okay, so and it turns out it works beautifully. You can just do the average, and now you get a theory with a large n expansion. You get some path integral with an n out front with some action for some fields. And if you take the saddle point of these fields, you get the Migdal-Dashberg equations now as a function of both momentum and frequency. So one of the things we have now done is just solve these numerically completely, Ilya Esklitz in particular, and the numerical and analytical arguments, which I don't have time to go into. I have only 4 minutes left, sorry. Tell you that the initial proposal of Patrick Lee is correct. This is in fact the correct solution of the fully self-consistent equations. Okay, so now things are looking good. We've just at some level just made the Patrick-Lee theory for a non-Fermi liquid systematic. And in principle, we can now look at corrections. Okay, so that's satisfying, but all right, it hasn't solved the strange metal problem. I'm not going to argue. So the next thing to do, and this is described in this paper on the archive, is take this theory and compute the conductivity. And this was done by Young, Beck, Kim et al. In this old and very well-known paper, and widely cited paper, by summing diagrams of this type. In our case, we don't have a choice on which diagram to sum. The large N theory tells us. And fortunately, it gives us exactly the same diagrams, plus all orders, higher orders of these types of diagrams. So from the analysis of these diagrams, which we now believe is not correct, they concluded that this is a strange metal in the sense that resistivity equals T to the 4/3, and which is strange enough. It's not linear, but close enough. And also that the optical conductivity has this infrared, mid-infrared behavior of omega to the -2/3. This comes out basically as a consequence of this omega to the 2/3 self-energy. But neither of these results is correct, even though they've been very widely used inside it. And the reason they're not connect is because they don't account for boson drag or phonon drag. Meaning that the electron can give its momentum to a boson, but the boson eventually gives its momentum back. Now, for the electron phonon problem, you can ignore this because the coupling is weak and the phonons will go out of the sample or hit an impurity or something. But here, the coupling is infinitely strong. It's so strong that there's no difference between the electron and the boson. In fact, neither the electron nor the boson exist. It's a non-Fermi liquid. So how can you say the momentum is carried by the electron or the boson? You can't. It's in the limit of infinite drag because the quasi-particles don't exist. And when you account for the drag properly, you find that both of these results disappear. The resistivity is actually 0. The DC resistivity is 0, as we've shown over the years. And somewhat more surprisingly, even the optical conductivity is trivial. It's still just 1 over omega, and the imaginary part is just a constant at best. And there's a recent paper by Senthil's group coming to the same conclusions with quite different methods. So I'm rushing here because I'm out of time. All right, so let me just, I'm up. Can I have 5 minutes here? So okay. All right. So what we have done is that this theory here, unfortunately, is not a strange metal, despite long belief in the literature. All right, so you have to break momentum conservation in some way. And so we said, okay, let's look at disorder. Let's put in some disorder. So the simplest disorder you can put is random potential Vij. This is the basis of a theory of disordered Fermi liquids. And the nice thing with this large N approach is it's very easy to incorporate this in the same large N approach. You're averaging anyway, so it's no trouble to break translational symmetry now and get somewhat more modified large N equation, which I'm not going to write down. Okay, you put in this disorder, and what do you find? That the Landau damping is now just mod omega, not mod omega over Q. Again, something well known. And when you put this in to the fermion self-energy, you get the marginal Fermi liquid self-energy. So this is a result, I believe it's already in the famous HLR paper. So that's exciting. Marginal Fermi liquids, you're on to something. It'll give you a T log T specific heat that you all see in essentially all strange metals. So maybe this is the solution. Unfortunately, it's not, or fortunately. If you plug this into these diagrams again, because even though you lost momentum conservation, the inelastic scattering is still forward. And there are, again, cancellations. And so you, in fact, find, even though this is a marginal Fermi liquid, unlike the claim of Verma et al., it is not a linear T. That doesn't mean there's a linear T resistivity. and resistivity is completely conventional. All right, so we were ready to just give up at this point. This whole line of thinking is not going to get us anywhere. But then we realized there's another place you can put in randomness. You can add randomness in the Yukawa coupling. You can add randomness in the disorder, in the interaction. That's the lesson of the SYK model, really. So now you have two types of interaction. There's the spatially uniform interaction, which is probably the larger term, and you have some weak modulation of it with G prime. You have G and G prime. And G now depends on R, and it's 2-point correlator as a delta function. Again, the same tricks work. You get saddle point equation, you solve them, and you get the same diffusive propagator, and you get two contributions to marginal Fermi liquid behavior from the G and from the G prime. But now you're getting somewhere because this thing doesn't cancel. It doesn't cancel between all these diagrams, and you get a non-Fermi liquid contribution to strange metal. In fact, what you get exactly what's seen. You get a linear T resistivity, you get a 1 over omega optical conductivity in the scattering rate. And you get the log enhancement of the effective mass. All of these things are seen in the cuprates, certainly, and many other materials. Okay, so I think I'll end there. So to summarize, if you take this theory of Fermi surface coupled to any sort of bosonic order parameter, and the main conclusions also hold for antiferromagnetic order parameters with finite momentum and so on. It seems we're still studying some details, and that there are three types of couplings. There's the spatially uniform Yukawa coupling. That does have a singular self-energy in thermodynamics, but it's a perfect conductor, or there are no singular corrections of the Fermi liquid transport. If you put in random potential, you're halfway there. You get a marginal Fermi liquid self-energy and a T log T specific heat, but nothing in the resistivity or the optical conductivity. But finally, if you put in random interactions in space, then you get everything you want. Okay, I'll end there. Thank you. Sorry, that was quick, but this is very recent work. I mean, I should say that I am fortunate to have some incredible collaborators here, Avishkar Patel, Al Hayugo, and Ilya Asperis, who all contributed, into the 60-page supplement of this paper that I urge you to read if you want to learn more about these results. Yeah. 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 Yeah, no, if you just add only the last thing, that is correct. That's the only thing we don't need, but then it's not physically a reasonable model. So I would say, so we are solving the theory in a certain large N limit. Now, in the large N limit, we have these three independent couplings. You have, or at least two independent sources of disorder. We have the V and the G prime. In the real world, they're not really independent. And so the picture is that maybe microscopically what you have is the V, but if after you do some density functional theory, you do some renormalization, that will generate some interactions in random interactions, because you go into some orbital that basis that diagonalizes the disorder, and the disordered basis, the matrix elements will all become random for the interaction. That's kind of the picture. But we don't have a systematic way of doing all of that. We're doing the large N limit. In the large N limit, you just have to put the needed types of disorder separately. But that's really what we want to do. I very much want to look at next, is to figure out, get some microscopic understanding of what contributes to this G prime disorder. But we're pretty convinced that this is really the disorder in the interactions is the key. It's remarkable how easily it just fits everything. Okay, maybe we're just too excited for very recent work, but anyway, so far we haven't lost our hope. Yeah.
It began life as a methodology that enables you to control vertices.
Yes.
Now I understand right, you're beginning to think that the disorder of the interactions is something that will, I guess, no matter how clean you make the system,
Yeah.
will scale up to some finite value or.
Well, I mean, eventually the strange metal will disappear. So I would love to see, somebody really improve the sample, not make it dirtier. Really improve. Again, the disorder seems to be key, and eventually, I would suspect that it will get Fermi liquid behavior if you make samples cleaner and cleaner. T squared will reemerge. That's the prediction. Now, I mean, so there's the fact that the theory without spatial disorder does not have a strange metal or even any kind of anomalous metal, I think is very clear. I have no doubt about that conclusion.
So,
Yeah.
I mean, in the strange metals we have the linear line, there's a huge number compared to residual resistivity.
Right.
Right. So how big does that huge rise have to get before we start to see? I'm saying hypothetically.
Yeah. So here I'm right. Let's look at this result as a function of frequency, but the same thing happens as a function of temperature. So just imagine this is rho of t and omega is t. Okay. So there's two terms. There's the residual resistivity, or the constant here, which is proportional to the second moment of v. And there's this term, which is proportional to the second moment of g prime. And so you could take a model where v is 0, and this is, so when a model where g prime is very large and v is small, will give you exactly that. It will give you essentially no residual resistivity and a large linear T resistivity. But why should v be small and g prime be 0? I don't have a good answer, but roughly I can imagine that you go to some new basis of exact eigenstates of the disorder. You start with some quasi-particles or fermions and bosons, go to some exact eigenstate basis, and then in that new exact eigenstate basis, v doesn't do much, but the g prime is still there. You can't get rid of it. You can gauge away the disorder in the quadratic part, but you can't gauge away the interactions. That's a very hand-waving picture. I'd love to make it more concrete, but that's the direction of my thinking. But if v is 0 to begin with, then you're not going to get g prime. V is obviously some potential due to dopants or something. That's always there. If we get rid of the dopants and somehow manage to dope something without disorder, well, this type of strange metal cannot appear. That's for sure. There's another way to fixing the problem with this theory, that theory, which is to put an ohm clock. And there's been nice papers by Patrick Lee and also by Eris Berg looking at the effects of ohm clock. Those all require some special accidents. Certain wave vectors have to be small, and those mechanisms all break down at very low temperatures. Yes, they do. And they don't give a T log T specific heat. So one of the things, a recent paper by Sean Hartnell and Andy McKinsey's emphasized that every metal that's a strange metal down to 0 temperature with linear T resistivity also has a T log T specific heat. And this gives you that. So I mean, the original, I would say the marginal Fermi liquid dream of Chandra et al., this is realized in this model. So I can say it's in this, you need the G prime, and then you realize it. Yeah.
You mentioned that strength of the image is controlled by G prime.
Correct.
But you know in experiments, what they look at the slope on this.
Well, so one thing that has been mentioned in many papers is that the slope of the resistivity somehow seems to correlate with TC, which is, so they certainly measure, it's very clear that it's a measure of this interaction, some kind of non-Fermi liquid interaction is the key thing. Then there have also been experiments where they do radiation damage, and what they find is that that seems to just raise the residual resistivity, but doesn't do much to the slope. So in our approach, we would say, well, I can't explain that, but at least there's enough room in this theory. We have enough free parameters to fit that. We have the V that determines the residual resistivity with the G prime that determines the linear slope. They're independent types of coupling. So at least there's room for them to behave differently. Exactly how they behave in a real system, yeah, well, we want to work on that. Yes.
Time we're going to have to carry on. We've had a discussion as well. We're going to have to catch up on the apologies to those online. And let's thank Subir for a great sequence.
Thank you.
Late, but we can get back together and
Subir, can I ask a quick question, if you have a sec?
Yes, I just want to introduce myself. Hi, I'm Dominic. I'm a student at RNG.